What's up, people? We're going to talk to you about intramolecular forces. Intramolecular forces. And this is going to be a short video, okay? Because there's going to be another video as well. When I say intra, it's spelled like this: intramolecular, okay? And that means inside the molecule. Let's think about a molecule. Let's think about pH3. Okay, I wonder what shape that would be. Well, let's see. It's covalent. We're going to expect it to be 3D. We would end up drawing it like this. Got an unbound pair up here, and the shape of that is trigonal pyramidal. I'm just throwing in some review here. Trigonal pyramidal, all right? And these are all sigma bonds, right? And boom, here it is. Look how quickly I built that. Here's a nice little marshmallow shape. It's three-dimensional. It's polar. It's got that end and it's got that end, right? It's got two different ends on it. So I guess I should have written that down. As a molecule, the whole molecule is polar in shape. It's a polar molecule. But when we talk about intramolecular forces, that means what are the forces that hold the molecule together? Well, those forces are these little bonds right here, right? These are the intramolecular forces. And the thing is, we can label these sigma bonds as being of three different types. And those three different types are, it could be a truly ionic bond. It could be a polar covalent bond, or it could be a non-polar covalent bond, okay? There's really not a dash here. Okay, now I told you this molecule we're working with right here is pH3, right? So let's look at this bond right here, this one right here. It's between a P and an H, and it's inside the molecule, so it's an intramolecular bond. We're going to see if this bond between the P and the H is an ionic bond, which we wouldn't expect because this doesn't cross the stairs, right? We're going to see if it's a polar covalent bond or a non-polar covalent bond. And there's a real easy way to do it. Ionic bonds, the difference between the electronegativity of the atoms is greater than the number 2. In a polar covalent bond, the difference between the two atoms, between the electronegativity of the two atoms, is between 0.5 and 2. And in a nonpolar, the most sharing type of covalent bond, a nonpolar covalent bond, the difference between these atoms is less than 0.5, okay? All right, so let's look between P and H. Well, conveniently on your test, and in every time I ever ask you about that, I'll give you Linus Pauling's chart of electronegativity. All right, now, let's see, we've got a P. Let's look up the P here. The P, if we look at the P, it says 2.19. Look right above the letter P. Okay, so the P is 2.19. And then the other one is an H. See that H? So let's look above the H here. 2.2. 2.2. Wow. 2.19 and 2.2. Those are very, very close. 2.19 and 2.2. Those are so similar. 2.2 minus 2.19. The difference is 0.01. 0.01 is down here. Truly nonpolar covalent. Now, what if we had another molecule that looked just like this, right? Another trigonal pyramidal molecule. But let's say it's NF3, nitrogen trifluoride. I'll draw a nitrogen trifluoride up here. NF3. It's still got that unbound pair up there, just like you would expect on this phosphorus right here. It's still trigonal pyramidal. But let's see how this molecule is held together. Let's look at the bond right here between the N and the F. So we have an N. We'll look it up. Above the N, it says 3.04. Okay. So for the N, it's 3.04. And for the F, we'll look up an F. It is 3.98. The F is 3.98. We subtract them, we'll find the difference. And the difference is 0.54. So we'll look at our chart. That's between 0.5 and 2. So nitrogen trifluoride, its intramolecular bond, the intramolecular forces, okay, are polar covalent. But for phosphorus trihydride, its intramolecular forces are nonpolar covalent. That's all there is to it.